All right, so why do we need object-oriented programming? You must have heard the phrase many times, and you must have heard that Python is an object-oriented language, right? Pretty much all the modern programming and all the modern coding revolves around object-oriented programming, right? Sometimes you might hear functional programming a little bit, imperative programming, right? All of these have been sort of embedded into an object-oriented paradigm. So there's three properties that are essential, and then they were recognized from a software engineering point of view to be very important for developing large code bases, right? Complex pieces of software. So these properties are encapsulation, right? You want to treat data or data with many attributes, right? Collections of many pieces of data as a single entity. All right, and in this way you want to perform abstraction, to hide. I was telling you at the very beginning that essentially it is easier to operate with abstract information, with abstract concepts, than with concrete ones. Why? Because the concrete ones are very hairy. They have a lot of details. And I was telling you that, for instance, the concept of infinity, right? It's abstract and many people have trouble comprehending it, but actually simplifies things in mathematics. It's easier to do math if you have infinity as a concept than if you don't, right? Because if you have infinity as a concept, any sum of any two numbers, right, will still be a number. Whereas if you have a finite range, you're not guaranteed that the sum of any two numbers will still be a number, right? So infinity gives you closure with respect to arithmetic operations. Right? And if you didn't have infinity, right, what would you do? You would have to look at numbers in a lot more detail. You would have to consider the case that you're adding two numbers, you're not getting back a number, right? You would have to always consider two cases. Oh, I'm adding two numbers and I'm getting back a number, or I'm adding a number and two numbers and I'm not getting back a number, right? Or you perform, as computers do, you perform modular arithmetic. So you're adding two positive numbers and actually getting a negative number. All these cases should be considered separately, right? There's more, it's more complicated reasoning when you don't use abstraction, right? So encapsulation allows you to do that, allows you to consider many collections of small properties as a single entity on which you define operations, and those operations essentially are simpler to reason about. All right, so that's one thing. And that is relatively easy to comprehend, and that is accomplished by many other means, right? We were talking about aggregation in Python. We talked about tuples, lists, sets, right, and dictionaries. And all these are means of aggregations. All these are means of putting multiple pieces of data into one thing, all right, and are thus means of encapsulation, right? All the means of aggregation. You don't necessarily need objects. But there's another thing that you need in object-oriented programming. When I was saying that you need abstraction, right? Abstraction means hiding details. Sometimes you need to hide them so that somebody else can't see them, all right? So you need access control to your data, all right? Why do you need that? You have to take this with a grain of salt, right? When developers work together in a team, the most costly thing is communication between them. All right? That's the most costly thing, keeping everybody on the same page. And you can imagine that the cost is generally quadratic. Every two coders have to sync and have to be on the same page. When instructions come down from the top, everybody understands a different thing, right? This is not like in English where, well, it's okay, we understand each other, right? You're talking about something that is slightly different than what I'm talking about, right? Because we have understood the same concept differently. Here, you have to talk to the computer eventually, right? And if my understanding is slightly different than yours, my code is going to do slightly different things than yours, will work on slightly different assumptions than yours, and then you're going to have a bug, right? So you have to make sure that everybody is perfectly in sync, and the more coders you have, the more difficult it is, right? So guess what you want to do? You want to not have to tell everybody everything. You want to say, oh yes, I'm going to design my entity, and I'm going to expose to you only this aspects of my entity, and the rest, I'm not going to tell them to you. All right. Obviously, any developer can go into my code and actually find out for himself. It's not a matter of really being secret, right? It's a matter of giving access. But the way I write code, if that developer, first of all, won't be able to change the stuff that I decided it's private, all right? And then the more important thing is that I designed it in such a way that he really doesn't need to know. In order to do his job, he doesn't need to know my private stuff. And in order to do my job, I don't need to know his private stuff, right? So you want to minimize the amount of information that you have to communicate with each other, right? So this is the concept of data hiding, of abstraction. And third is code reuse. And code reuse seems a relatively simple thing to do because you can put everything in procedures, and I use somebody else's procedure, then I reuse code. Actually, it's a lot more complex than that because you want to have fine granularity in code reuse. I want to use 90% of your code, but I want to change one little thing, right, that is not at the top level of your code, right? So in order to make that apparent, let me try to draw a little thing, see how successful I am, right? So software often is written hierarchically, right? So there's a pyramid, right? At the low level, you have a bunch of procedures, and then on top of that, you have some other procedures that are calling the lower layer procedures, right? And then on top of these, you have a bunch of other procedures, right? And maybe here at the top, finally, you have one procedure that represents your API, right? Your big operation that you're coding, right? Which has, it's a procedure with some parameters and can do certain operations and so on, right? So you have these dependencies, and let's say I want to use, and what happens, right? This guy calls the next guy, right? And the next guy, so let's assume some procedures here as well, right? So there are calls here. This guy calls into the next level, and from each procedure you have calls into the next level, and then you have calls into the next level, right? So there's this layer. 5 is actually a very small number of layers. Usually have something like 30, right? A full-fledged API would have somewhere between maybe 30 to 50 layers, and of course it's not that balanced. So on one side it's shallower, on the other side is a lot deeper, but it doesn't matter, right? The important thing is that now I like this library, this collection of procedures very, very much, but I don't like this procedure right here. This one is the one I don't like. Okay, how do I replace it? It's not very simple, right? If I made it, if I made my procedures in such a way that this calls this and this calls this, right? Typically, I mean, what you would say is, oh, I go into the code and I change the calls into these objects. I change them into calls to a different procedure that I want to be the replacement of the current one, right? But actually, what happens most of the time is that you don't get the source, right? Code is proprietary. When I want to use somebody else's code, what I get is a binary, or I get something that is obfuscated. I don't get the full code because those people worked on that code for years and got paid a lot of money, right? So whoever owns the code doesn't want to give it for free. Once they have given away the sources, it's like the code can be replicated, an unlimited number of times, and essentially whoever buys it only once, and then can distribute it to everybody else. So what you want is to embed a mechanism, which is called virtual methods or virtual linking, right? Dynamic linking, which allows the replacement of such procedures at runtime on the fly. So we're going to see how this happens in objects, right? This is a very important thing. So each procedure now becomes an object, right? And an object, through its inheritance mechanism, can perform replacements of arbitrary methods at runtime as needed. Let's try to experience a little bit of object-oriented programming. So remember three things, right? So aggregation, right? Encapsulation, which is essentially data hiding, and code reuse. Of all these, right? Aggregation and aggregation was solvable by other means, but encapsulation and code reuse, in the flexible way that object-oriented programming allows it, are not available through anything else. Okay, but the first thing that we want to experience is the concept of state. What we can hide, and we haven't seen yet, what we can hide inside an object is the concept of state. So we're going to define a bank account. All right. Now, when we have objects, we need a way of producing objects, and we do that by means of a blueprint, which we call a class, right? This is something that will lead to a class of objects, right? Think of that. But the class is essentially a scope that contains code pertaining to this object that we're about to build. And the procedures that we put inside the object are called methods, all right? And they have the property that they operate on the object by default. Okay, so we have a few very important things here. One is the constructor. This procedure or method with this very special name, underscore underscore init underscore underscore, is the initializer. So what happens is that later we're going to say variable, we'll pick a name for it, let's say account1, is equal to bank account, and what we want initially here is the balance, right? So what happens is, whenever such a call occurs, is that the memory pertaining to this object that's about to be created is allocated by the system, right? It's not the job of the class to allocate the memory, but this memory is completely uninitialized. It's like empty, right? The concept of empty memory doesn't quite exist, but it's untouched in a way, right? Whenever it's untouched, it still contains something, possibly zeros, but whatever it was left after the computer was initialized. But it's untouched. It contains data that is random. It doesn't contain data that is useful, right? So this area of memory is passed into self. This piece of memory that the system says the object is going to be here is passed into this self, right? And we want to add stuff to this self, right? Self, like, this is the class, and it's creating an object. An object operates on self, on itself, right? So we're going to say that self should have an attribute called balance, which should be equal to initial balance. Initial balance being the argument passed in as the argument of the constructor, right? Whatever is passed, the number passed in as an argument. All right? And then this is stuff that we design: deposit and withdraw. All right? So from an account, we want, the most basic operations would be to deposit some money, withdraw some money. Right? So if I deposit an amount, I need to increase the balance by that amount. if I withdraw, right, I need to deduct, right, from the balance that amount, provided that there is enough money in the balance, right? So we're going to check if the balance is greater than amount, then we allow the deduction, right? Otherwise, we stop. And this probably should be greater or equal. Okay? So let's see what happens when we execute this code. Where do we do that? Okay, so I'm going to do this directly in idle. All right, so typing this in defines a class. We don't have any object of this class yet, right? So we're going to say account 1 is bank account. Let's say we put in $1,000, right? So now A1 has the money inside, right? So that's the concept of state. There's a state inside A1. Right? A1 doesn't change per se. I'm not saying A1 is assigned something, but if I say A1 dot deposit another $100, all right, that works. And at all times, I can query the balance. Right? We can see that it's 1100. A1. Let's withdraw 500. Right, and again, if I say A1 balance, I'm going to get 600. Right. Now, what I would like to do is avoid A1 balance equals minus 10, let's say. And this is something we can't do right now, right? So we would like to be able to hide the balance from the client, right? So we are playing two roles now. Typically, this part of the code is written by somebody, one programmer, and these pieces of code are written by somebody else. All right, so this is the user, right? Here, this is the user or the client of the API. So this is a misuse, right? I am permitting the balance to be negative when it's clear that that doesn't make sense, right? And when we wrote the program, we actually created this withdraw method in such a way that it wouldn't be able to reach a negative balance, right? But because we couldn't hide this balance, right, we have that problem. All right. So let's see what's next. Interestingly, we can create two accounts. So now. You see, if I do A1 dot deposit, and I can add another 100, let's say, and then now if I say you want A1 withdraw, which is, and I'm trying to withdraw, say 1,000, right? It will yield an error and tell me that it can't withdraw, right? So these are correct operations, deposit and withdraw, the balance here is one that is not intended, right? It means that the design of our class is not great, but it's halfway there. Okay. Interestingly, we can have a separate account, and that's the important aspect of objects, right? I can create a second object called A2, and then this A2 will have a completely separate state, right? A2 is completely independent from A1, right? If I operate in A2 on A2, right, I will get 500, and the balance of A1 is still 90. All right, so one thing that we haven't seen before is exceptions. All right, so whenever an error condition occurs, we want to signal that to the system in a very specific way. All right, we can do it in a variety of ways. We can return a string saying, oh, this is an error, shouldn't do it this way, right? But the most usual way of dealing with an error, right, is by raising an exception. And exceptions have a very specific handling mechanism, which is very different from handling legal values that are returned from methods. And this is the syntax, right? We raise, and we raise something that is an error. We have many predefined errors in the system. We can define our own, but you'll rarely need that, right? If we say dir of, let's say just dir, I'll get this once where there's built-ins, dir built-ins. Okay, so you see they're ordered in alphabetical order, right? Going by the old order where the capitals, all the capitals are smaller than all the lower caps letters, right? So all the values that start with a capital, they are at the front, and you can see that all these happen to be errors, right? Up to here, no. So all of those that have the word error in the name, those are errors, right? So you have to look very carefully which one would apply. In this case, it's a value error because we received the wrong kind of value, and that's what we return. You see value error is here. So it's very easy to pick an error that would be adequate for handling your error condition, right? Now, what do we do with these? So let's say we want to use an account in a different piece of code, right? We want to handle errors gracefully in general, right? We don't want this very messy message, right? So apart from the fact that it's a messy message, right? It's hard to understand for somebody who's not a coder, right? It also stops your program. So if you would have a procedure calling another procedure, calling another procedure, calling another procedure, right? And let's say you want to do a loop and perform multiple operations. So on the first exception, the entire program crashes, right? So what you want is what we call catch the exception, right? And handle it gracefully, right? So a way to do that is using this construct called try catch. So try, and then we perform this operation that potentially leads to an error. And if an exception occurs during this operation, we catch it. This except clause catches a specific type of exception, right? We get the value of that exception. Typically, we would put a string inside the exception, right? And that string will come here, and we can print it nicely and at least create a nicer interaction with the user. Okay, so let's try this. I can't remember how much is in A2. I think it's actually more. So you see, this doesn't lead to an exception yet, but I can keep trying. Right, so still didn't lead to an exception because I think there's $500. So let's check now A2.balance. There's 100 left. So I can still use this code to withdraw. This operation so far hasn't raised an exception yet, right? But now it will. Exactly now, because there's 0 in the account, it will, right? And you see, instead of the red message, you see a much nicer, much more readable message, which is the message that we have provided here, right? So we're printing encountered error, which is the string here. And this is the message that it's still us, but the coder, right? We're the client now. When we do this, we're the client, right? And we're saying that whoever wrote this is the coder, right? So the coder put there this message. And we are extracting this message and presenting it to the user in a nice form. Okay? So now this is wrong. We should prevent it, right? In Python, actually, you can't really prevent it, right? In most OOP languages, you can prevent it by simply declaring balance private. All right. What happens, what coders do in general is, instead of naming an attribute like this as balance, they will name it with 2 underscores, underscore balance. And by convention, this is private. You're telling other developers, you don't need to know anything about this and don't touch it. All right? And because Python is supposed to promote civility. People are supposed to be civil to each other, right? So you're supposed to just tell them. You're not supposed to enforce it, right? Languages like Java, C++, pretty much every other programming language, you would say private balance, right? And that effectively hides it from other developers, meaning that once you set private on a balance, this expression, the compiler will choke on that expression. We'll say, you're trying to access a field that is private, stay away from it. So that's what we use. Whenever you want to have something private, you just put double underscore and you use that variable with double underscores in front of it. It's private. All right, let's try to understand inheritance, right? So remember, inheritance is about code reuse, and it's about the ability to replace a procedure at runtime, any procedure of an object, with another procedure. So we're going to start a hierarchy of persons, right? So we're going to create a person, and we're going to assume that the only attributes that we're interested in are the name and the date of birth, right? And we endow this object, this person, with the ability to say something. right? Of all the things that a person could do, right, all we care about is their ability to say something. So we could create people like this, right? We could create a person, Jack, with this date of birth, another person, Jill, another date of birth. We can evaluate their name and date of birth, right? So this person.name will evaluate to Jack. This person.dob will evaluate to 2nd of February 1996. And one thing we can do is ask a person to say something. All right, so person2.say, the sky is blue, and what will happen is that we're going to say Jill says the sky is blue. Okay, so let's experience that. I want to not have it so low at the bottom of the screen. Sorry, Control V. So we create a person, and I'm just going to copy very quickly because I don't want to type, especially on this keyboard. So let's create the two persons. All right, so we have person1, person2. If we say person1.name, we get Jack, person2.dob. One strange thing that also it's not possible in many other programming languages, but for instance, it's also possible in JavaScript. You can add attributes. So I can say person1 attributes after construction. Right, person1.gender equals male. Right, so now 1.gender will be male. Person2.gender does not exist. Right? If I ask person1 to say the sky is blue, what we get is Jack says the sky is blue, right? And we can do the same for the second person, right? What you have seen here is as an error is just another exception, right? So we could have trapped that into a try except statement. So I want person2.gender, right, except, and attribute error, right? You see here. So we're going to say except attribute error as ERR. And what we want to do here, we're going to say print encountered okay. So this is nicer than this. But also, you know, if you're inside some sort of a loop, this will get printed and not crash your program, whereas this will crash your program. You won't execute the rest of the loop, right? But rather the program stops here. Okay, let's see if we can define a different kind of person. So let's try a student, right? So a student is a sort of person, right? And when we're saying is a sort of person, it has everything a person has plus some more stuff, right? And we're going to say that a student has a major, right? So what do we do typically? Because, I mean, we're saying that, right, a student is a person, right? We should first initialize the person part of the student, and only once that has happened, we should initialize the remainder of the object which is specific to the student, right? So we're going to want to build a student out of a name and a DOB, because without those it can't be a person, and a major, right? So what we're going to do is invoke the person's constructor, right? This super will send us to the person, and out of the person we invoke the constructor init. This init, if you remember it here, would take only two arguments, right? Name and DOB. We always write the self here to just remind ourselves that we're operating on the current object, right? But only what follows is the actual arguments. So we're passing in the name and the DOB. All right. Whenever we define the method, we have to pass in the self. Whenever we use the method, we don't have to pass in the self. That's another sort of strange thing with Python. And then we also have to take care of the major, right? So once this object has been initialized and the name and date of birth are set, right, we can set the major. So this constructs the object, and this is the only thing we do, right? So the student is still able to say stuff. All right? So this is a way of inheritance. We're inheriting the same method from the person. All right? So I can construct the student, I can check their major, which is going to be psychology, but the interesting thing is that now I can say bill.say the sky is blue. Okay. And what is going to come back is Bill says the sky is blue. Right? It will appear like this. And I think there's going to be no quotes. Okay? So let's create another kind of person, a lecturer, right? So the lecturer is a person with the ability to lecture. So it has everything that a person has, plus a new method called lecture, right? So we can expand an object or a class in multiple ways. We can either add new attributes, or we can either add new methods, or we can add both attributes and methods. All right? So the lecturer is a type of person, and because we don't have any new attributes, we can rely on the same constructor. We don't have to create a new constructor. We're inheriting the constructor, right? But what we have on top of everything is this ability to lecture. And when we lecture, when the lecturer lectures, right, it actually says things, because lecturing is not so different from saying. But whenever a lecturer is asked to lecture on S, he will say S exactly using the way a person says anything, right? And the lecturer will add, you should be taking notes. Okay? So if you take Razvan as a lecturer with the name Razvan, who was born many years ago, all right? and we ask Razvan to say the sky is blue. Right? You see, the say, we're not asking Razvan to lecture, we're asking Razvan to say, right? The say method exists because it is inherited from the person. And what you're going to see is Razvan says the sky is blue, as any other person would do, right? That's what saying. However, if we ask Razvan to lecture the sky is blue, Razvan is going to say the sky is blue, and after that Razvan is going to continue saying you should be taking notes, right? Because the lecturer says the thing he's lecturing on, and then he adds you should be taking notes. Is this clear? Yes?
Also, don't you have to compare to the student? Can you go up to the student?
Mm-hmm.
How come in the lecture you don't have to do init self-name?
Because I haven't added any attributes, right? Since the attributes are still just the name and the just the name and the date of birth, right? Whenever I'm performing this, right, what happens is that we're getting the chunk of memory for the object, and then Python is going to look for an init method, and it's going to look at, oh, does the lecturer have an init method? No. Does then the person have an init method? Oh yes, I'm going to use the init, right? So essentially we always go down the chain, right? Because a person might be built on top of another class, which might be built on another class, right? So when you're saying, I want to use this method, right? It will go and say, oh, does the top class have it? Oh, if not, let me go to the one underneath. Then let me go another level down, right, until it finds. So this is what we call symbol resolution, right? It can be method resolution or it can be attribute resolution. Whenever we try to invoke a method, right, we have a search order for these. Okay? So notice the distinction. Okay? So now let's define a new type of class, right? So an extra level, the arrogant lecturer, which is a type of lecturer. All right? And the arrogant lecturer has a different say method. So this is where the very interesting thing happens, right? So it has a different say method. So forget about the say that a person has, right? In doing that, we're actually saying that it overrides a base class method, right? And we're asking the super to say, so we're still relying on the person, right? This is the say from the person. We're still relying on the person, but this say is going to start with, it is obvious that. And we're going to take this phrase, but we're going to turn it into lowercase so it doesn't look weird with capitals in the middle of the phrase. Okay? Now Einstein had the reputation of being a very arrogant lecturer. All right? So we're going to call him Albert, right? So Albert, arrogant lecturer. It's not quite 22 centuries ago, but it's the 19th century, so it's, yeah, in a century that is 2 centuries ago. So now if we ask Albert to say the sky is blue, all right, Albert is going to say it is obvious that the sky is blue, right? Because this is what we defined. Right, so this is very interesting because we're reusing in a very complex way, right? So we're defining a new say that relies on the person's say, but because we called it the same at the level of Albert, the person's say method is no longer visible. There's no way at this point, if my only point of reference is Albert, there's no way to invoke the person's method. The only thing I can invoke is Albert's say method, right? But while we're in here inside the class, we actually have access to the person's method via super, right? So super is the lecturer, which doesn't have a say method. So when we try to find the say of the lecturer, we don't find it there, we go one level down, we find it there, right? Now, I should have said earlier, rather than now, this class that we put here in brackets is called the base class. So the arrogant lecturer has the lecturer as a base class, the lecturer has the person as a base class, right? The student also has a person as a base class. And if we're checking this relationship in reverse, we say that the arrogant lecturer is a derived class of lecturer, right? So arrogant lecturer is derived, lecturer is base. But in being base, lecturer is in fact a derived class of person. Cool. So the interesting thing is, what's going to happen if we ask Albert to lecture? So you see the answer there. Usually I would not show the answer and everybody would be wrong. Okay? So we're asking Albert to lecture The Sky is Blue, right? We're going to the lecture of, we're trying to find the lecture inside here, right? None. I am going to the lecturer. And the lecturer is going to say. Which say do I go to? I go to the say of the self. But the self is an arrogant lecturer. So I'm going to go to this say. I'm not going to go to this say. So the search for the method always starts from the self, right? The self is Albert. When you call say, the self here is Albert, right? So it's somehow strange because you're essentially calling lecture. Albert, right, dot lecture and Albert and argument, right? So this is what becomes the self, and this is hidden here, right? So whenever I'm calling a method, the first argument, the self, it's hidden, but it's still passed in. Python will pass it in for us, right? But you have to remember it's there. So this is Albert, the arrogant lecturer, right? So what's going to happen is we're going to go to lecture here, right? But lecture invokes the say of the self, and the self is the arrogant lecturer. So we start from the arrogant lecturer. So we're going here and say, can we find a say here? And since we do, we're going to use this one, right? And then as we go inside here, we see, what's the super? Oh, the super is a lecturer. And now when I say super say, this is different from self say. Super is a lecturer, so I have to go to the lecturer. And I have to, so what happens at this point when I said super is that this guy is a lecturer, is no longer an arrogant lecturer. So I'm going to say self say, and does the lecturer have a say? No, I have to go to the base class, which is the person, so I'm going to use the person say to say something, right? So because of that, the output is, right, it is obvious that this comes from the arrogant lecturer, right? Then this comes from the say. So it is obvious that, right, this comes from from the arrogant lecturer, right, which adds this, okay? Then this comes from the say of the person, And then this comes from the say of the arrogant lecturer. Sorry, from the lecturing of the lecturer. That makes sense?
Sorry,
yes.
Repeat.
So it is obvious that comes from the arrogant lecturer, the say of the arrogant lecturer, right? So it is obvious that this string will be created by the arrogant lecturer. You see the plus here, so this string is created by the arrogant lecturer, right? And we have to use the say of the person. So this will come from the say of the person, right? But then we're still inside the lecturing, right? The lecturing is inside the lecturer, and the lecturer says whatever was here, which is it is obvious that, and it has to add, you should be taking notes. This say will come from the arrogant lecturer. This self is still Albert. So we go here, right? We're going to create a string. It is obvious that you should be taking notes. Okay? And then we're going to use the say of the person to put that on the screen, right? And in putting that on the screen, the say of the person will add this part. Right? Because that's what the say of the person is doing. Let me go back here. Right? So this is what the self of the person is doing. It says self.name, which is Albert, says, and then whatever it is to be lectured or said. So you see, in effect, what we have done, right? In effect, what we have done is we have replaced the same method of the lecturer. Right? So the arrogant lecturer replaces the same method of the lecturer, but the arrogant lecturer is written later than the lecturer. At the point of writing the lecturer, we had no idea how this class was going to be used. Right? So we're writing this class, we're putting it out there, and then somebody comes and say, oh, you have 3 methods inside, but I don't like the 3rd method. So let me selectively replace it. All right? So in this way, they are able to customize the software, right, in a way that it actually fits their needs. All right? So this is the strength of object orientation. It allows selective replacements of codes, and if the code was very well designed from the outset to what should allow to be replaced and what not, right, these small punctual replacements will allow customizations that you, as an original designer of that code, could not have thought of. You see? Okay? And this is essential in today's software design. You wouldn't be able to do it without object-oriented programming. Does it make sense? If you got this, you got object-oriented programming. Yes?
So it's sort of like the arrogant lecturer almost changes the say of the previous,
Yes.
the base.
Right? It changes the say, but you see, so yes, but you see, the say is used. So the lecturer uses the say. And your go-to thinking is, oh, I'm going to use the say of what has been defined before, right? Which is the say of the person. Actually, not true. I'm going to use the say of the self that is being passed in, right? And that self can come with a different say, which I'm still going to invoke, whatever it is. Right?
Yeah.
So you can have an object with 100 methods, right? Calling each other in a very, complicated pattern, And then somebody comes and says, oh yeah, it does almost everything I need to do, but except, you know, if I could just change this function, this 10-line function, this 10-line method, if I could just change it, right? Well, you can. What do? You create a new object that has so I create an object that has your object as a base class, and in that new object, I change one method. I add one method, which overrides the one in your class. Then all your methods, whenever they invoke the method with that name, they invoke my method and not the old method. Okay? This was a huge advancement in software engineering. And note that I'm saying software engineering and not computer science, right? It's a very practical concern, all right? And the more you practice, you know, programming for the real world, the more you understand that this is essential, and without this, a lot of software would not have existed, right? So the advent of C++ essentially opened the door to large-scale software development, yeah, you have the software you have today. Cool. All right. Since we don't have a lot of time left, one thing that I was going to cover is the way we can use operators, right? So far, you've seen, and I'll probably not need the editor anymore, you've seen that I can write 1 + 2, and this is evaluated, but 1 is an object coming from the class int, all right? But it's a bit stupid to say x is int 3, which I can do, and then x is 3, but and whenever I say x is assigned 3, in Python will figure out that, oh, 3 is an object, so let me pass it to the class int and actually create an object, right? So then I can say x dot add, let's say 4, right? So whenever I write x plus 4, Python notices that I'm using plus, and it will, under the hood, convert it into this. So guess what now? If I create a class that has a method called __ add __, right? Which, what does this __ tell you? It shouldn't be used directly, right? So in public programs that you would submit anywhere, if you do that, you will not be liked. And we're doing this just for experiment, right? So it's not meant to be used this way, but nevertheless, this is what Python does under the hood, right? Guess what? You can actually define, there's no restriction in defining a method called __ add inside your class, because inside a class, a method is allowed to be private. So I'm going to say addable. All right, and I'm going to, let's say we have an init. We should have an init. Self, and let's take a string s, and let's just store it for the time being. Self dot data, and actually we don't need on both sides, is s. Right, so we're essentially storing s, so we can do something with it. Def add. All right, and we're going to take in a self. and say we take another addable a. And what we're going to do is return self dot data plus self dot, or maybe maybe we can reverse it. How is it? Is it reverse? Plus a dot data. I'm not sure if this works. So let me make sure that reverse reversed. Okay, cool. So let's go back to this and actually correct reversed. All right, so now I can say, right, x is addable, and we're going to put a string here, a, b, c, and y equals addable, d, e, f. And what happens when I say x plus y? Well, we're going to get the first string reversed, followed by the second, right? So I can define the plus operator between arbitrary objects, right? And I'm not restricted to the plus. I can do it with any other one, right? So if I say dir of an integer, right, you can see and probably guess easily all the operators, right? So you have add, you have and, right? So whenever you do that's the bitwise and, right? So if you have say 5 and 7, not a good example, 9, you get 1, right? So if you say 5, whenever it's a digit, you have to put in brackets, and 9, you get the same thing, right? So this is internally converted into this. Therefore, if you define the method and inside a class, automatically objects of that class will be able to use the operator and, right? So this will make your syntax potentially a bit nicer. So whenever you operate with objects that have behaviors like addition, for instance, you write a library for matrices, right? And matrices, you can add them. So it will be interesting to create a method underscore underscore add underscore underscore, and then you can say matrix A plus matrix B, and you get matrix C, right? And that will look a bit more user friendly. You can, and you can experiment with all of them. Interesting, you have sealing, right? So this is what the seal method. So if I say seal of 4.5, oh no, math.seal. of 4.5, right? So actually math.ceil invokes 4.5. Float doesn't have attribute ceil. Really? Then what's ceil for an integer? What I'm trying to say is that not everything is an operator, right? So sometimes you have standard library functions, but they're actually invoking methods inside they're just a shortcut for a method inside the object, and so on. So this can make your programs a little bit more user friendly, and they can look like you are designing your own language, right, rather than just writing procedures. Cool. Okay, so that's about it. Yes.
So like the thing that makes it easier is if you define the underscore add underscore, you can just use the plus.
Yeah.
Right, as a replacement. So, but then how do you know what symbol corresponds to what thing you define?
You kind of guess them, right? There is documentation, so you can use the documentation, right? But you can kind of guess that this this is greater than, this is less than, less equal, less than, modulo, which is the percent sign, right? Unary negation is neg, right? Unary minus versus binary minus, right? So unary minus is neg, binary minus is sub, I think. And some operations are reversed, right? So you can, if, for instance, if sub is not available, I think you can use R sub. Which means that it's invoked on the second argument. Yeah. So this is something nice to play with. It looks like an extension to the language. You can't change the precedence, though, right? So star multiplication has still a higher precedence than plus. Therefore, you should actually use this trick only in the case where you're working on objects that resemble something that has algebraic properties, right? Are similar to plus, similar to multiplication. You shouldn't apply them arbitrarily to some objects that you're inventing, because then it's going to be very confusing, right? It might not, the precedence might not make sense there, right? And then it's imposed by the language. There are languages where you can define arbitrary operators. Like for instance, you can define the arrow, and like in Scala. In Scala, you could say something like def this, and this is the name of a method, right? And then I don't even need to. The dot is optional, right? Instead of writing a dot arrow, I can simply write arrow. Right, so Scala doesn't have that problem, and I can do that with any method, right? I can say instead of a dot method, I can say a method, right? So a dot method applied to b, right? This becomes a meth b. So Scala would be clever in that way, right? And then if I put a arrow here, right, might mean implies or function definition, or something that makes sense mathematically. Cool. We're going to try next week to look at a little bit more of real world Python. So we're going to look at data that we extract from the government statistics site. Right, and we're going to do some stats, We're going to get some data about demographics and try to process it and plot some graphs. Okay, that pretty much concludes, or I was going to conclude the course. Please watch the videos that I uploaded for the week when I was away, right? If you feel that there's a need for me to redo those classes, I can do it in the last week. All right, so I'm fine with doing it. There's absolutely no problem for me. It's your time availability that is of concern here. Okay, so let me know. Please try to watch that. Cool. Lesson is over, class dismissed. See you next time.